So today we're going to talk about limits, which is what 12.1 and 12.2 talk about. And limits pertain to graphs of functions and where the graph is approaching at a particular x value. So here's your definition of a limit. It's a little bit of gobbledygook. You've got if the function of x, which could be any equation expression that you can think of, becomes arbitrarily close to a unique number. So when we've graphed certain graphs, you've noticed that the left-hand and right-hand behavior have gone in a particular direction, and maybe they approached a particular asymptote, or the x or the y-axis. That's what it's talking about with a limit. We're trying to see, well, what is that function approaching at a particular value? Is it approaching 0? Is it approaching 3? Is it approaching -5? What's going on? So that's the number that we're looking for, L for limit. And then as x approaches c, c is the number that we're looking at for the x value. And then we're going to determine what the y value is. L is your y value of the function. C is the x value of the function that we're looking at. From either side, we're going to also look at left and right-hand behavior. Some limits do not exist. And so then we'll look at a left-hand limit versus a right-hand limit so that we actually have some sort of a limit. But this is your notation that you'll typically see. So the limit of f of x as x approaches some number c is this value L. So we have several different methods that we can use. The easiest method is your substitution method. So for this function, x squared plus 2x minus 5, what is the limit as x approaches 4? So one method is just a substitution method. We're going to evaluate that function at 4. So if I plug 4 in for x, don't I get a value of 19? If you look at the equation or the graph, so take your calculator. Oh yay, my batteries are low. We'll see how that works. All right, so I've got y equals, I'm going to put in x squared plus 2x minus 5. I'm going to hit graph. Oh, I think I'm zoomed in. Yep. So make sure you have your standard viewing window. So there's my parabola, and I want to know what is the limit as x approaches 4. So on our graph, here's 1, 2, 3, 4. That's the x value, that's your c. I want to find out what y is as it approaches it. Well, can I see y on this particular graph? No. Where could I see it? Table. So if you go to your table of values, so second table, if I put in 4, don't I get 19? So that's just direct substitution. So example B is the same thing. What is the limit of this function as x approaches 4? So if I put 4 in for x in all 3 places, I evaluate it and I get 19 thirds. Your calculator probably isn't going to give you 19 thirds if you try to use it. So if it's a fraction answer, I want the exact fraction answer, not the decimal equivalency. All right, so there's that. Then we have a whole bunch of properties that are kind of no-duh properties. They do make sense based upon your experience that you've had so far. So again, think of it this way. If we're taking the limit of some number b, that's your function. It's an actual number b. So let's say you're taking the limit of, look at the example over here, 14. If the function is 14, isn't the equation y equals 14? Right? This is your x value quote. And so if I don't have any variables in there, isn't this a horizontal line going through the y-axis at 14? If you put into your calculator 14 and the y equals, you're going to get a horizontal line at 14. And so what is the limit as x approaches 5? It doesn't matter what the x value is, what's the y value always? 14 on a horizontal line. And so that's why this particular property says if this is a number, the limit is whatever that number is. This particular property says that if you have just x in there, as x approaches c, if I use substitution and replace x with c, won't the limit be c? Look at a real number here. Here it is. I want the limit as x approaches 4. Replace x with 4, don't you get 4? So that's just a very simple function. Same thing here. If I've got x to any exponents and I'm approaching c, I'm replacing x with c, and so you would just take that number and raise it to that exponent. So for example, I've got x cubed here. I'll know the limit of the function as x approaches 2. If I plug 2 in for x and raise it to that third power, I'm going to get 8. So the limit is 8. And if you look at the graph of x cubed, really hold that thought. First time it gives me that notice and then the batteries are totally gone. Your calculators show a low battery forever before they actually run out. Now let's try it. So now I have x to the third. Now I hit graph. And I want to know the value of the function as x approaches 2. So here is 2. As I go up here, could it possibly be 8? Just because I can't see. 1, 2, 3, 4, 5, 6, 7, 8, down to 2. So it does approach that. What about square roots? Or cube roots, or fourth roots, or whatever root it might be. So if you have just a plain x under there, this is supposed to be a little beta. You're going to replace x with that number that x is approaching, in this case c, and just take the root of that. So in this case, we're taking the cube root of x as the function approaches 8. So the cube root of 8 is 2. So those are easy. Question? I can't hear you, dear. This very first one? So if the b is just a number, so they use b instead of x because it's going to be a constant, some number. And so here's an example here. If my function is just 14, when I take this limit notation off and make it into an equation, y is equal to 14. Just like up here, if I took the limit notation off here, y is equal to x squared plus 2x minus 5. Okay? So if y is equal to 14, that's going to be a horizontal line going through the y-axis at 14. Okay? And so therefore, it doesn't matter what the x value is. The y value will always be 14. Does that make sense? Okay. All right, so then look at operations with limits. So essentially, we can multiply our functions. If I multiply my function by anything, b again is a constant, all I have to do is take the limit of that function and multiply it by the same constant. So over here, if my function is 10, so both of these functions are just constant numbers, 10 and 5. So the limit of this function is 10. Wouldn't you agree? Because it's a constant. So if I wanted to know the limit of 6 times that f function, 6 times 10 is 60. So obviously these are very simplistic functions. I could easily have x squared minus 4 as a function. Whatever the limit of that x squared minus 4 is, it depends on what value of x that I'm looking at. I would just multiply it by 6. Same thing goes, I can add and subtract functions. I just add and subtract the limits. And so I've given you an example over here. I can multiply functions together, and so I would just take each separate limit and multiply those limits together. There's your example over here. Division, same thing. And then I can take a function, an entire function, and raise it to an exponent. And then I would just take its limit and raise it to an exponent. So flip that, and let's look at some true, real examples and some other methods other than substitution, because substitution doesn't always work. So let's look at, and this is where your calculator is going to come into play. Again, let's look at finding limits with a table. Because if I try to use substitution here, when I'm finding the limit of this function, when x approaches 1, what's going to happen? What's going to happen if I substitute 1 in? What was that? I have a denominator of 0, don't I? If I plug in 1 here, I'm going to have 0. You can't have 0 in a denominator, so you won't be able to define that limit. So do you remember when we were graphing these way back in semester 1? What would this cause us to have on our graph? What's that thing called? A hole, or how about an asymptote? Remember those? We had a whole thing about whether we had a vertical asymptote, a horizontal asymptote, or a diagonal asymptote. Remember those? Well, or sometimes there's a hole in your graph. So we have a different way that we can approach that. So go ahead and take this function and let's plug it into our calculator. So we're going to put it into y equals, use parentheses. So parentheses x cubed minus x squared. And if I type something in wrong, you gotta let me know because I can't read with these glasses on today. And parentheses, then divided by parentheses again, x minus 1. So then hit your graph. So it resembles a parabola, but there's going to be a hole in the graph. Does your calculator show the holes? No, some of yours do, but most of our calculators don't show the holes. So I don't actually see a hole here at 1. So right here on the graph, there should be a hole, but you don't see it. But what I can do is see it in my table. So if I hit table, and I start plugging in these functions, here's my limit right here. So you have to decide what numbers you're going to plug in for x. My limit at 1 should read an error. So if I put 1 in here, I get an error because it creates that 0 denominator. So I want to go slightly to the left of 1, which means smaller, and slightly bigger than 1, to the right of 1, bigger. So you could go 1.0001. You're kind of limited to what types of numbers that you can put into your table here. I mean, if I had my druthers, I'd put 0.0000001 because I want to get as close to 1 as possible, but not exactly 1, because then I won't get a 0 in the denominator. So I have chosen values. Typically, I'll choose 0.97, 0.98, 0.99, 1, and then these. But you're not going to be able to type all those in, so let's just start with 0.97. Whoops, I want to go up. So 0.97, 0.98, 1, there's my error. Because you want your limit that we're approaching in the middle, the number that we're approaching. And then 1.02 and 1.03. Oh, we probably could have gotten 0.99 in. So as you look at the numbers, from here, if I approach from the right, which means going from the right of 1 towards 1, so I'm really going in the left direction, what's happening to this value? Is it getting bigger or smaller? It's getting smaller, right? Towards what number? It's getting closer and closer to what number? 2. Then we hit the error, we skip over 2, and then this number is getting smaller this way, which makes sense because it should continue to get smaller. But if I approach 1 from the other direction going this way, isn't it getting bigger and bigger and bigger until it approaches 2 but doesn't hit 2 because of the error? So my point is, the limit as x approaches 1 is 2. You can see that on the table here, because as these numbers get closer and closer and closer to 1, they're getting closer and closer to the number 2. And you can see it on your graph. So if I go back to graph, I can actually look at my graph and identify, here's 1 on my graph, and if I were to go all the way up to the graph right here and go all the way across to here, isn't that a value of 2 for y on my graph? Even though there's a hole there, as the graph comes this way, it's approaching that value for y of 2, and as the graph comes this way, it's approaching that y value of 2 again. Yes? Oh, okay, so if your table's not allowing you to type in, you want to go to table set. So you want to go to second window, and then see where it says independent, that's your x variable. You probably have it on auto. You want it to say ask. And then you want the dependent to be auto, so it'll automatically calculate it for you. Okay? You guys good with that? Okay. So then hit second quit, so come back out. So then let's look at this next one. So again, I want you to put this function into y equals. So clear that out. Oh, is there? No, that's exactly what I want you to put in there. So when you put in your 1/2, you're either going to put in 0.5 or you have to put the 1/2 in parentheses. So I'm going to put my 1/2 in parentheses. And then if I just look at the graph, I can, just based upon the graph, if I look at where the graph is approaching, as x approaches 4, 1, 2, 3, 4, so here's 4, draw a straight line up, this is where it approaches, or this is where it touches the graph. So if I look over at the y value, isn't it hitting a y value of 3? Yes or no? But if I put 4 into that graph, it's not, there's no hole on the graph at 4. Couldn't I still use direct substitution? True or false? I could still use direct substitution, but my point is, whether or not there's a hole in the graph, I can still use my table. So go into the second graph and look at your table. So I want you to put this time to the left of 4. So notice I'm still using 0.97, 0.98, 0.99, but I'm putting 3 in front instead. And I've got 01, 02, 03. So those are the numbers you typically are always going to choose. And so we're going to go ahead and put those in this time. 3.97, 3.98. So 4 does not get an error this time. That is your exact limit, because that's substitution. So this one we could use either way. But I just wanted to point out to you that your table is going to show you the same thing as direct substitution shows you. So as you approach 4 from the left, going towards it, it's getting bigger and bigger and bigger until it hits 3. And then as you approach 4 from the right, it's getting smaller and smaller and smaller until you hit 3. So your table of values shows you the limit of that function as it approaches a particular x value. And then the last one on here. Don't I get an error for this function as x approaches 3 if I plug it into the denominator? So again, if you were to plug this into your calculator using parentheses here and parentheses there, these are the values you're going to get. This one's a little bit more difficult to see what's happening, because most of you are probably going to tell me that the limit is 0.17. Am I correct? Doesn't that look like what the table's telling you? So I always will plug it into my calculator and look at the graph as well. So I want to explain to you why the limit on this one is 0 and not 0.167. And so let's go ahead and plug that into our y equals. So it's not always cut and dried. So parentheses x minus 3 divided by parentheses x squared minus 9. graph. So this is what our graph looks like. And as x approaches 3, so here's, well, it's hard to tell, but here's 1, 2, this is probably about 3 right here. What does it look like the y value is? If you were to guess just by looking at the graph. It's not, isn't the x-axis an asymptote? So this graph, as it gets bigger and bigger and bigger, as it approaches infinity, isn't it going to approach 0? It'll get closer and closer and closer and closer and closer and closer to 0. And so on this particular one, if you see a graph that looks like this, and your table of values shows you that, your answer really should be that the limit is 0. So that's a much different graph than the graph that we had previously on either one of those. So note to self, you might want to highlight that and put on their C graph to understand why it goes to 0. All right, so then we can also just look purely at graphs, and I have put a link on my website to the Khan Academy where you can practice looking at graphs and finding limits. And if we have time, we'll explore that today as well. But let's go into y equals. We're just going to put these functions in. Again, we could use direct substitution. If I put 3 in for x, 2 minus 3 is negative 1. True? And if you look at the graph, and I've graphed this for you, so clear that out, put in 2 minus x, and it's a straight line. So all I'm trying to tell you is as x approaches 3, so here's 3. Down here, if I approach the graph in this direction at 3 and I hit straight down, I'm here at negative 1. Same thing, if I approach the graph from the left and I hit 3, the y value is negative 1. That's all that you're looking for. Look at this one. If I plug in 3 minus x, here's what my graph looks like. It hits the x-axis at 3 and the y-axis at 3. As I approach the graph at 2, it's hitting this value here on the graph, which has a value of 1. And again, with direct substitution, if I put 2 in there, this one, however, uses pi x over 2. So this tends to be on our circle, isn't it? Our unit circle. And it's multiples of pi over 2. So as x approaches negative 1, if I plug negative 1 in here, I get a negative pi over 2. But if this is on our unit circle, think of where negative pi over 2 is. Where is negative pi over 2 on your unit circle? Isn't this right here negative pi over 2? What's the ordered pair? This is 0, negative 1, right? Okay. So we're going to put this in our calculator, but because of the pi and the x, so go ahead and go into y equals. I want to show you what happens. First of all, make sure that your calculator is in degree mode before you start. I just want to show you what happens if it's in degree mode. So go to mode, and I want you to highlight degree, and then go to second, quit, or you can go to y equals, I guess. Clear. Then where's your pi button on your calculator? It's above the, it's not your second, is it? Oh, I can't read it. Oh yeah, it is second. It's because I can't read that tiny. So seconds, I'm going to do parentheses. Seconds, caret, x, divided by, maybe I'll do parentheses, divided by 2. Here's what my graph looks like. Interesting. What if it doesn't look like that, does it? No. Because your calculator thinks in degree mode that this is decimal equivalency value, right? So it's like it's half of pi, so whatever half of 3.14 is, that's your coefficient. That would be a linear function. But your calculator should be in radians. So go back to mode, highlight radians, and go back to graph and see how your graph changes. Oh, it did not change. Seriously. Fascinating, really? Okay, go to Zoom. 7. Still, seriously, wow. I don't know why it's not working. Oh, thanks. Thank you, because I can't see. I knew I wasn't going totally crazy. Yeah, it is the sign. Doi. All right, so go back into here. So sign. Then, oh, good. Don't have to redo it. So it should be a sign. Oh, yeah, actually I do. Divided by 2. Okay, so that should make all the difference in the world. Now graph. That's much better. So that's a little harder to see. You might want to zoom in. So hit zoom and then in. Enter. And isn't that your typical sine function? Now if you trace, this is not going to show up as pi over 2, pi, 3 pi over 2. Pi, you might want to wake up because you're not doing yourself any good. If you think about, isn't this cosine and sine here? Isn't the sine of negative pi over 2 negative 1? So as our limit approaches negative 1, in other words, if I put negative 1 in there, the value of this is the sine of negative pi over 2. So that value of the sine of negative pi over 2 is indeed negative 1. And if you look at the graph, here's negative pi over 2. As we approach that value, the sine on that sine curve does have a value of negative 1 at that lower dip of the curve. Because remember, its range goes from negative 1 to 1. Caitlin? Sine, cosine, or tangent. See how we have the sine here? You might want to put, where's my red pen? Orange will do. You might want to put parentheses around here so you can see. With my eyes today, I totally missed it. Yeah, but you can still, you can still do it in radians. Okay. So watch what happens on the next one. So on the next one, if I just keep my calculated radians, I'm going to go back to zoom out. And then we're going to go to y equals. Take that out. This time I have absolute value. Where's the absolute value found at? Math button, right? And then where on there? Number, right? So hit enter, and then you get x plus 2 in there. And then go outside of that, divided by, you need to use parentheses, x plus 2. Do those cancel each other out? Do these cancel out? Nope. And notice that our limit is approaching negative 2, because what does negative 2 do to the denominator? It makes 0, right? Now hit graph. So this is still zoomed in a little bit. I'm going to go back to my standard. Well, we'll go ahead and keep it there. So I drew your graph. There are holes on your graph that your calculator doesn't show here and here because x does not have a value of negative 2. But as the graph approaches negative 2 from this direction, what is the y value? What is it? 1. As it approaches from this direction, what is the value? Negative 1. Do you see how this is your right-hand limit. The right-hand limit is positive 1. The left-hand limit is negative 1. If the right-hand limit and the left-hand limit do not agree, the limit does not exist. So there is not always a limit at every x function. Now, having said that, I could have a closed dot up here to close in that. It doesn't matter. Your left hand and right hand behavior will still create that limit does not exist. All right, so then let's look at more limits that fail to exist. So I've given you some more comparisons here. So Square root of, or the absolute value of x over x gives you the same situation because your left and right hand behavior do not agree, the limit does not exist. This one's interesting because although I don't have a hole in my graph, isn't the y-axis an asymptote? Right? Because the graph is approaching the y-axis, but it is never going to cross it. Mostly because can x be 0? No. So as you approach the graph from the right, isn't the graph increasing without bound? I can't tell you what the y value is because it's increasing without bound. And same thing, as I approach the graph from the left, it's going to increase without bound as you hit 0. It's never going to actually hit 0. So anytime that you approach a graph from right or left and it's increasing without bound, the limit does not exist. And then this one's fascinating. Go ahead and put this one in your calculator. It's the sine of 1 over x. Make sure that you left your calculator in rad mode. And start with a standard viewing window. So go back to your standard viewing window because most of you will have that. And it'll look a little weirder. I'm going to zoom out a little bit. So go into y equals, put in sine of 1 divided by x. It'd be nice if we didn't have a glare. So right here, it looks like a little blip on a heart monitor, doesn't it? So when you see that, and we're approaching 0, so it's right here, you're like, something's going on here, I can't tell. So go to zoom in, hit enter, and now all of a sudden you see this oscillating behavior. Zoom in one more time, so hit zoom in, enter again, and then the more you zoom in, now you can see that really oscillating behavior occurring. And so that's why I drew this for you. Anytime you have oscillating behavior as x approaches a particular number, the limit does not exist. Because your right hand, your left hand limits won't really agree. All right, so then let's look at 12-2. So 12-2, we're just going to look at some additional techniques other than substitution, looking at a table, or looking at your graph to find a limit. So here we have, oh, and I put out the divide out technique. The divide out technique you can only, you really should use when direct substitution produces a 0 in both the numerator and the denominator. So not just the denominator. Use this method called divide out when it occurs in both places. So if I were to put 0 in here, well, this one doesn't actually happen, right? If I put if I put -3 in here, what's -3 squared? 9. Plus a -3 is 6. What's 6 minus 6? 0. And then if I put -3 in here, that's 0. Do you see how I have 0 over 0? So the divide out technique just means, in this case, I can factor the numerator, factors into these two binomials, and then the denominator is not factorable. But now it cancels out, right? And I'm left with x minus 2. Now I can use direct substitution. And so you might want to highlight the fact that we took the limit here of -3 and substituted it in here for x. So I would highlight the -3, the x, and the limit here of -3. So all I did was put -3 in there for x minus 2. So we're taking direct substitution and combining it with this method called dividing out. And I end up with a value of -5. If I actually look at that graph, so I'm going to go back to my standard viewing window. So if I put this in parentheses, x squared plus x minus 6 divided by parentheses x plus 3. So as we look at this graph, it actually looks like a straight line. As x approaches -3, so here's 1, 2, 3. If I draw a vertical line through there, this is where the y value is going to occur. 1, 2, 3, 4, right here at -5. Isn't that what we got through the divide out? And of course, your calculator is not going to tell you that there was a hole in that graph there at -3. All right, look at this one. Sine of x and tangent of x. As x approaches pi over 2. So all I did was view at pi over 2, isn't the ordered pair 0, 1 on the unit circle? True or false? Okay. Isn't this cosine sine? So all I did was replace sine with its value of 1, and then tangent, isn't tangent sine over cosine? So down here for tangent, I put sine over cosine, which technically is undefined, correct? Whenever we have a fraction in a fraction, don't we take the numerator and multiply by the reciprocal? So that's all I'm doing here. I'm taking the numerator, 1 over 1, put it over 1. I multiplied instead of divided by the reciprocal of 1 over 0, 0 over 1. Didn't I get a value of 0? If you plug that into your calculator in radians, you should see that as x approaches pi over 2, which is your first hash mark, that it should be hitting the x-axis at pi over 2, meaning it has a y value of 0. All right, this one's a little different. You've got a bigger denominator than the numerator. Again, if I put 1 in here, I'm going to get 0 in the denominator, 0 in the numerator. This is one that you're not used to dividing. You could either use group and garbage, group these two, group those two, take out a GCF, right? Or I just use synthetic division. So I took all the coefficients here, put them across here. I'm going to divide it, but it's kind of reverse division. I'm going to divide it by the x minus 1. Always the opposite sign, so since it's minus 1, I'm putting in 1 in for my synthetic division. So I brought it down. I should get no remainder because this should be a factor of this. So that means that now I have x squared plus 1. So I have an x minus 1 over, remember I divided it by x minus 1, times what was left here, x squared plus 1. These cancel out. I'm left with a 1 in the numerator over that x squared plus 1. Now I can use direct substitution. And so I'm replacing for x1. So I put 1 in down here, and so I get a value of 1/2. Then we have this rationalizing technique. The last time that you learned about rationalizing was when you had a radical in the denominator. Well, this time we have a radical in the numerator. You could also have it in the denominator, but if I plug in 0 for x, I'm going to get 0 over 0 again. So when you see a radical, use your conjugate. The conjugate just means you multiply by the same thing, but you have a plus or a minus in there. It should look like the difference of two squares factor pattern. So since this, I started out with a minus, my conjugate is the same thing but with a plus in the middle. Be really smart. You could FOIL this, but isn't this the difference of two squares factor pattern? Doesn't it factor as a squared minus b squared? Right? So what's this squared? The number under the radical. So the radical disappears, x plus 1, minus what's this squared? Just 1. So that's where that came from. Over x times all of this. Notice I didn't multiply it out, and if I were you, I would not multiply it out. Then the positive one and the negative one actually combine and cancel each other out. So what you're really left with is x over the x times that. Don't the x's actually cancel? That's why you should not multiply the denominator out, because you're going to get something to cancel with your numerator. And so I end up with this final expression. It's okay to have the radical in the denominator. We're unrationalizing it, so to speak. Now I can use direct substitution. So now I'm going to substitute the value that we're approaching, which is 0, in for x. And the square root of 1 is 1, plus 1 is 2. So it actually has a value of 1/2. The second one, again, I'm using the conjugate. Since that's a minus, I put a plus here. This is your difference of two squares factor pattern. This squared is y plus 5. This squared is just 5, and you have a minus in the middle. A squared minus b squared. And then this times this, don't multiply it together. Leave it unmultiplied. The 5 and the negative 5 cancel out. You end up with a y in the numerator over that denominator. The y's cancel, and now you have this expression here. So now we're going to use direct substitution. Substitute in for y, that's 0. You cannot take the square root of 5. 0 plus 5 is square root of 5. What's square root of 5 plus square root of 5? Doesn't that give you 2 square roots of 5s? Okay, your book is going to accept this as an answer, as your limit. If I were you, I'd be rationalizing it and multiplying it by rad 5 over rad 5. But this is the answer that's going to probably be listed in the back of your book as the limit. But in my opinion, it should be rationalized. All right, so then the last one on this page, we can approximate a limit. So on this one, as we're looking at, if you were to put this in your calculator, which I'm not going to make you do, but as I approach 0, I get very nearly the same number. We can take the two numbers that are very close to 0. Notice this time I didn't use 0.97 and 0.98 and 0.99. I use, well, mostly because it's not 1, I guess. I use really close ones as far as I could put in my calculator. You could go out to four decimal places if you want to, and your table will read that. Anyway, I got these two numbers, these two values for y, just average them. And that will approximate your limit. So there's your limit approximation. Same thing over here. If I put this in my graph or my calculator, it has to be in rad mode. And then that's what your calculator is going to show. As the graph approaches from the right, it's going to hit 1. As the graph approaches from the left, the y value is also 1. So you could approximate using your graph as well, and we've talked about that too. Questions on that front page? Okay, so then look at the back. So we've talked about limits that do not exist when the left and right hand behavior do not agree. So as you look at this particular graph that I put down here for you, if I plug this into my calculator and look at the graph, as you approach from the right, the limit is 2, right? As I approach from the left, isn't the limit negative 2? So when the left and right hand behavior do not agree, the overall limit does not exist. But you might be asked instead, look at the change in notation here versus here. They're saying, what is the limit of the function f as x approaches 0 from the left? So if you have a 0 with a little exponent of a negative, it's asking you for the left-hand behavior limit. And so this one over here is asking for the right-hand behavior limit. So the limit on the right is 2, limit on the left is negative 2. So we can actually find partial limits if we only approach from one side for a limit that does not exist. Remember these piecemeal ones? These ones are harder just to put it in your calculator. So if I were you, I would choose values based upon your limitation and just plug into here and plot those ordered pairs. So for this one, 4 minus x, you can only choose x values that are less than 1. I would, of course, always choose 1 because notice that your limit down here approaches 1 because that's where we're switching off here. And notice that there's no equal sign on this range or this domain. And so that means technically that there is no value for x at 1. There should be a hole in the graph, which is why I put a hole here. So at 1, 4 minus 1 is 3. So at 1, the y value is 3. There should be an ordered pair there, but because we can't equal 1, I put a hole. Then I chose another value less than, so I chose 0. That gives me 4, and so I just drew my line this way. You should know that it's linear. Then on this one, I plugged in 1 also. I again got 3 if you plug in 1. Then I plugged in 2. So 4 times 2 is 8. Minus 2 squared 4 is again 4, right? So we're going up. This is a quadratic, so it should look like a parabola. And then I plugged in 4. 4? 1, 2, 3, 4. Yeah, so I plugged in 4, and that gives me a value of 0. And so I've got my shape to my graph. And as you can see, as x approaches 1, there goes my marker, from the left, as x approaches 1 from the left, it does hit a value of 3. So the overall limit on this one actually does exist. As x approaches 1 from the right, it goes up, 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 and it comes back down as it gets closer to 1, and it hits a value of 3, well, close to it. So the overall limit on this one actually does exist because the left and right hand limits agree. So the first one, the limit did not exist because left and right hand did not agree, but the overall limit here does exist. Last thing, do you remember the difference quotient? Remember how much fun that was? Well, you're going to want to know and master this difference quotient because it's how you're going to do the shorthand cut. Shorthand cut? That doesn't make any sense. Anyway, there's a shortcut to finding the equation of the tangent line. The equation of the line tangent to your parabola. Remember we did that and we didn't like that problem? But we're going to use derivatives. Derivatives involve the difference quotient. And if you don't know how to do the difference quotient, you can't do things the shorthand way. So here, we've got the function of x is x squared minus 1. Here's your difference quotient. You've got the function of f. You're going to replace every x in the function of f with 3 plus h. So there's only one x here. So you're going to take the whole function and write this as is. So I wrote this as is, but instead of x here, I put the 3 plus h. Then you're going to subtract the function, but you're replacing x with 3. So here's the function again. I'm subtracting the whole thing. It's got to go in parentheses, but instead of x, I've replaced it with a 3. These are the same function here and here, but this x is replaced with 3 plus h. This x is replaced with 3. And then the denominator is h. So if you go through and square this, you get 9 plus 6h plus h squared. It is not 9 plus h squared. Remember, it has a middle term. Minus 1. And then distribute your negative into here. This is 9 minus 1 is 8, so it becomes a negative 8 over h. In the numerator, the negative 1 and negative 8 is negative 9, and it cancels out with that positive 9. That means you're left with 6h plus h squared over h. If I stopped right there and did direct substitution, and my limit as at h approaches 0, wouldn't it be 0 over 0? Right? So remember we use the dividing out method if you get 0 over 0. So essentially, I'm going to factor this. I can factor an h out of the numerator. So that's what you see me over here doing. I'm factoring an h out of the numerator, and I get 6 plus h. The h's cancel. Now I can use that direct substitution and put in the number that I'm approaching, in this case 0, and I get a limit of 6. Now, the last thing I have to show you is, let me switch to my computer. So, oh, I didn't want that. This I do want.
Contestants,
Oh,
find the limit of this
oh,
equation.
hang on, stop.
Calling somebody else back.
Where's my... Hang on, I gotta plug in the noise. Now try this.
Contestants,
There we go.
find the limit of this equation.
Calling somebody else fat won't make you any skinnier. Calling someone stupid doesn't make you any smarter. And ruining Regina George's life definitely didn't make me any happier.
Your
All you
assignment's
can
on the
do in
board, by
life
the
is
way.
try to solve the problem in front of you.
The limit is -1.
Oh crap, I lost.
That answer is incorrect. We are in a sudden death. If Miss Heron can answer this problem correctly, we have a winner.
Limits. Why couldn't I remember anything about limits? Limits. That was the week Aaron got his haircut. Oh god, he looks so cute. Okay, focus, Katie. What was on the board behind Aaron's head? If the limit never approaches anything, the limit does not exist. The limit does not exist!
Our new state champions, the North Shore Mathletes.
See, someday this will be useful to you all.
How do you like me now? Like that? Yeah! Get some! Get some!
All right, guys, have a good afternoon.